Hi, I'm Nithin, and this is Aboudi. We're going to be talking about our physics engine PIES today. So PIES is a particle and constraint-based soft-body physics engine for simulating hyperelastic materials. We integrated our physics engine into Maya with the PIES for Maya plugin. These are some of the resulting animations we were able to create with the plugin. In this animation, we see two hyperelastic gears slipping as they attempt to mesh. In this animation, we see a rotating stiff rod winding the connected elastic string. The principal goals of PIES and PIES for Maya were achieved. We wanted to bring the convincing and robust elastic simulation possible with Projective Dynamics into Maya. We also wanted to be able to directly ingest Maya meshes, simulate them with acceptable default parameters, and allow for comprehensive tuning of physical behaviors and solver parameters. We also wanted a reasonable integration into existing Maya workflows. The core user features in PIES for Maya are the following. Users can create a PIES solver and adjust various settings like iteration count, step size, gravity, friction, and more. Users can also create PIES soft bodies and PIES cloth from Maya meshes. Various stiffness and material parameters can be adjusted to tweak the object's behavior. For example, the strain resistance and volume preservance can be adjusted for soft bodies. Bending and stretching resistance can be adjusted for cloth objects. In addition, users can create PIES constraints and PIES links. PIES constraints can be used to pin regions of physics meshes in space and constrain their motion over time. This can be seen in the bottom right GIF. PIES links can be used to tether two separate physics objects as seen in the rod and string example previously. Our physics engine solver implementation is based on the 2014 Projective Dynamics SIGGRAPH paper. So this is a huge simplification, but I think it conveys the right intuition about projective dynamics. In PPD, constraints are resolved by projecting particle positions from a violation state into a compliance state. Projection just means to fix a particle's position so it no longer violates a constraint. Well, in projective dynamics, instead of projecting positions directly, we simply create a virtual spring between the particle and the corresponding projected position. Of course, a particle may have several virtual springs attached to it if it has several constraints attached to it. This leads to a mass spring system matrix that can be solved to complete an implicit Euler time step. Finally, we'll go through a user workflow by Aboudi.
In this example, we start by creating a simple gear mesh and transforming it to a desired orientation. We want to make sure to decrease the subdivision count of complex meshes such as this gear so that we can keep a reasonable triangle count and keep a reasonable simulation time. We go to the PIES menu and create a default physics solver and select the gear and create a soft body mesh. Now we create a couple of other objects, in this case some toruses, and we select all the toruses and convert each of them into soft body meshes with one click. Now click on the gear and we can go into the soft body node associated with it and increase its stiffness. And that's how simple it is to create a soft body simulation with PIES. Now we're going to constrain one of our toruses to move in a prescribed manner. First, we add a PIES constraint to the scene, which shows up as a locator node, and we transform it to the part of the torus that we want to grab by and keyframe it to translate and rotate over time. The torus will then follow this motion. Once we're happy with our keyframed locator motion, our simulation can be updated to reflect these applied changes. Notice how the torus constrained to the locator is moving in the keyframe motion that was prescribed, and how the other objects are interacting as they normally would, falling down to the floor. That's all we have for this presentation on pies. Thanks for watching.